Hello, and welcome to the Big Bang. Two very important things to understanding kinematics: angular momentum and moment of inertia. Do you remember when we talked about a force creating a moment? When a force is applied perpendicular to the position vector from the origin, we get the moment about the origin from the position vector crossed with the force. The magnitude of this moment was the magnitude of the position vector times the magnitude of the force. When we had a couple, which involved equal and opposite forces applied to a body separated by a distance d, the magnitude of the moment was d times the magnitude of F, since the moment would be the same regardless of the point from which the moment was taken. The idea of taking these moments is important and gives you the intuition to understand moment of inertia and angular momentum. Let's now go ahead and tackle what these two are. The moment of inertia is sometimes referred to as the angular mass or the rotational inertia. We represent it by the capital letter I. The moment of inertia stands for the effect of masses on rotational inertia. You should be thinking, but how do these masses oppose rotation? If we have a body for which we want to calculate this moment of inertia, we can start by selecting specific axes for which to calculate I. Then all masses within the body will be accounted for as well for the distances between these masses and the axes. The moment of inertia can be calculated by summing all the masses multiplied by the square of their respective distances from the axes. Note that this is for a specific axis, and ideally for a rigid body you would be taking the integral and not summing the masses, which only gives you an approximation. Knowing the moment of inertia will allow you to calculate the angular momentum, which is quite literally the angular version of the linear momentum, m times v, we talked about before. The angular momentum L equals the moment of inertia times the angular velocity. If you think of I as a mass and the angular velocity as a velocity, you should see the similarity. We can rewrite the angular momentum by having r cross the mass times the velocity v. For calculating the angular momentum with n particles, we just have to incorporate the summation from 1 to n and get the position vector, the mass, and the velocity for each particle. We will see how the two definitions relate later. With the moment of inertia reminding you of mass and angular momentum reminding you of linear momentum, we can write down an angular Newton's second law. The sum of all the moments equals the derivative of the angular momentum with respect to time. We can then replace the angular momentum with the moment of inertia times the angular velocity. Since the moment of inertia is a constant, we take that out of the derivative and take the derivative of the angular velocity, which equals the angular acceleration. This should remind you of Newton's second law, where the sum of external forces equals mass times acceleration. Now, with a system with n particles, we take the derivative of the other definition of angular momentum, where we have the sum from I equals 1 to n of Ri cross mi times vi. When we take the derivative of mi vi, we get the mass times the derivative of vi, which is the acceleration. Thus, d dt of mv equals a force. As a result, we get that the sum of all moments equals the sum from I equals to 1 to n of Ri, the position vectors, cross Fi, where Fi represents the external forces. Let's explore the angular momentum a bit more. Picture this rigid body in plane motion. It has a center of mass g in the reference frame xyz. At point pi within the body, moves with velocity vi. The position vector Ri connects the center of mass to this point pi. We know already that for a system with n particles, we can represent the angular momentum as such, where mi is the mass of each particle, and you would in theory want to integrate instead of add up all the angular momentum. Let's replace the velocity vi with one of its definitions, omega cross Ri. we now have a vector triple product. And using the vector triple product rule, we learn that the triple product simplifies to the angular velocity times the particle position squared. Since we can move the angular velocity out of the summation, we are left with Ri squared times the mass of each particle. Do you recognize this definition? That's the moment of inertia, or the angular mass, or the rotational inertia, wherever you want to call it. This means that we can write the angular momentum as the angular velocity times the moment of inertia. And this allowed us to move from one definition to the other. Plus, if you need the derivative of the angular momentum, it is now easy to multiply the moment of inertia by the angular acceleration. Hopefully, this has given you an extra set of tools to use in kinetics and problems with rotations. And I will see you next time.